Imagine falling into a realm where the gravitational pull is so extreme that our mathematical models for reality cease to function. The first landmark on this descent is a boundary of no return, known as the event horizon. The event horizon is the specific distance from a black hole where the escape velocity required to leave exceeds the speed of light. Once you cross this invisible threshold, the laws of physics dictate that no amount of energy or thrust can reverse your trajectory. As you fall deeper, the sheer force of gravity begins to act unevenly on your body. This diagram shows a geometric shape experiencing a gravitational gradient, which is the rate at which gravitational strength changes over a specific distance. Because the gravity pulling at the bottom of the shape is significantly stronger than at the top, it gets pulled faster, stretching it vertically in a process called spaghettification. Eventually, the extreme tension overcomes the structural integrity of the object, tearing it apart into a single thin ribbon of individual atoms. This total disintegration of physical matter is merely the preamble to a deeper, logic-breaking mystery residing at the absolute center. This photograph shows Albert Einstein, whose general theory of relativity provided the first classical description of what might exist at a black hole's core. This animation illustrates the concept of a singularity. According to classical math, a massive star collapses into a point of zero volume and infinite density, creating a spot where the dimensions of space and time essentially cease to exist. When equations produce infinities like this, it signals a mathematical dead end. For modern physicists, a point where reality simply stops is an unacceptable answer, driving the search for a more functional framework. By 2026, a growing number of theorists have begun moving away from Einstein's model of a terminal center. This animation visualizes a modern alternative called the quantum bounce. In this model, the collapsing matter rushes toward a distinct, hard boundary rather than an infinite point. This is based on the principle that matter and information cannot be compressed into absolute nothingness. There is a physical limit to how tightly particles can be packed together. When the core reaches this absolute limit of density, the compression stops. The packed matter vibrates with immense potential energy, stored at the very edge of what physics allows. This stored energy triggers a massive physical recoil. Instead of freezing in place, the matter rebounds outward with explosive force. This replaces the image of a silent, frozen graveyard with a highly kinetic environment of constant motion. The core is redefined as a powerful engine of transformation, turning a massive collapse into a violent outward expansion. If matter violently rebounds instead of vanishing, physicists have to account for where that energy is actually displaced. This diagram shows the wormhole hypothesis. Under this theory, the extreme gravity creates a tunnel that channels the rebounding matter into a different timeline or universe, where it is expelled through an outward-flowing exit called a white hole. This shifts our understanding of black holes from cosmic trash cans to a complex interdimensional transit system. Moving these ideas from pure math into reality requires hard observational evidence. In 2025 and 2026, the James Webb Space Telescope, which observes the universe in infrared light to see through cosmic dust, captured a series of unexpected signals from the deep past. This deep field image shows specific anomalous glowing red dots scattered among early galaxies. Astronomers identified these as the little red dots. Using spectroscopic analysis, a method of studying light to determine an object's mass and temperature, scientists found that these dots represent massive black holes existing in the very early universe. These objects already held millions of times the mass of our Sun, just a few 100 million years after the Big Bang, growing far faster than classical physics suggests should be possible. The existence of such massive objects so early in cosmic history challenges our standard growth models, providing a data-driven incentive to explore the quantum theories that describe black holes as more than just dead stars. This animation illustrates a new possibility. These fast-growing black holes might have acted as seeds, using immense gravitational pull to gather ambient gas and dust. Instead of an endpoint, they appear to be the foundational anchors allowing the first galaxies to assemble. Our understanding has shifted from a graveyard for matter to a potential doorway to other worlds, a mystery that remains hidden until we